Hello, welcome everyone. So this is the second talk of this colloquium series today, and it's a pleasure to have Professor Sven Olaf Moch who will give the colloquium today. And before we start, I would request Professor Ravindranath, Director, to kindly introduce him and say a few words about it.
So welcome everybody. So it's indeed great pleasure to have Professor Sven Moch with us for our series of lectures that are, aimed at to celebrate 60 years of IMSC. So I am here to actually introduce him to all of you. Many of us know him from his works, and this is mainly for those who are not doing particle physics and those who are young, even if they are doing particle physics. Sven graduated in Germany from University of Hamburg, and then he became scientific assistant in Hamburg again, DAISY Hamburg. From university to the DAISY went, and then later on he moved to NICEF as a research associate, later on to Karlsruhe in Germany. And then he got a senior scientist position. I think that is where I met him for the first time, in Zeithen, in DAISY Zeithen in Germany. Then after that, he moved to full professor position in Department of Physics, University of Hamburg, Germany, and he is currently working there as a senior scientist, senior professor. And to its credits, he has won several awards. He's a leader of Helmholtz Young Investigator Group in Helmholtz Foundation, Germany. He also won Marie Curie Actions ITN Award in 2011 to 2014, and then later on he also was one of the chair of very prestigious meeting. It's called Biannual School of Computer Algebra and Particle Physics, called CAP, and then he also won the award of MTA Distinguished Guest Fellowship by Hungarian Academy. So these are awards that I can list for. About his scientific achievements, okay, he is one of those who actually made contributions to precision physics in a very big way. I mean, many of the computation, often we have one or two works to claim that we have done some state-of-the-art works in our lifetime, very few also. But Moch actually is just the other way around. One person doing many state-of-the-art works actually. There are computations that even after 10 years nobody has reproduced it actually. So those are that hard computation that he has actually achieved, and they are very useful for precision studies. Today we think standard model is really a standard model of particle physics, simply because of such precision computations done by people like Moch. And to his credit, actually he had computed for the first time 3-loop splitting functions, 3-loop coefficient functions in QCD, and also he was involved in top quark physics in a big way. Today we know top quark mass is some number simply because of all the hard works done by theorists and experimentalists. And also he worked on Higgs production, vector boson fusions, and things like that. And he is one of the authors of this famous ABM PDF fit. Actually, PDF is Parton distribution functions, which are very important to actually to predict observables at LHC, also other collider experiments. And he was involved in fitting those PDFs with his collaborators, and this is one of the well-known PDFs in physics actually. And he is also interested in threshold physics and physics beyond standard model and stuff like that. Actually, I also have common interest with him, and that's why he's here for some time. So I will not take too much time of his talk. So I request Sven to talk about what he's planning to talk, precision challenges in particle physics. Thank you.
Yeah, thank you very much for the kind introduction and for having me here. It's a pleasure. It's the first time in Chennai. I'm enjoying it very much. Great place. The title of the talk, as I said, Precision Challenges in Particle Physics. And just to set the stage, this is basically what we're interested in. This is just the, let me see here. Yeah, we have some pointing. So this is basically our table of elements, if you wish, in particle physics. It is has three families of quarks and leptons, and the gauge bosons, which are the carriers of the forces. Since 2012, we have also the last missing cornerstone in the original formulation of the standard model, discovered the Higgs boson, which is given explanation for the origin of the masses of the particles. No? So now the question is, all those particles are described by a couple of numbers, like their charges that they have under the local gauge symmetry, the spin that they have, and of course the mass. So you may ask yourself, what is the mass in particle physics? How do we go about? And of course, speaking of a mass of a body, this is a classical concept, which basically dates back to Newton. So it's basically the quantity of matter which arises jointly from its density and magnitude, and a body twice as dense and double in space is quadruple in quantity, and this quantity I designate by the name of body or of mass. This is what Newton wrote down in his famous definitions, and since then this is basically what we're using. It also went then on into atomic theory. If we go to smaller scales, so basically still at the level of atoms, we can basically try to count the number of bodies we have, the constituents we have there, sum them up, and call it a mass. And then this is also entering definitions in the International Unit System. So up to 2019, the mass was actually defined by a block of alloy of platinum and iridium, which is the original, has been stored in Paris in some vault. They took it out once every few years, and then they checked whether the kilogram is still a kilogram. But of course, first of all, it doesn't relate to any of the other physical principles that we had. And then secondly, the original kilogram, if compared to copies which had produced at the same time about 130 years ago, turned out that the kilogram was getting lighter over the time compared to its copies, and so this of course is also not a pleasant system. So this is why since 2019 we have a new definition of the kilogram, basically relating it now to quantum physics aspects, namely to the Planck constant. So basically saying a kilogram is now a body which has a certain, with which you can have a certain mechanical power, and you can equate it to an electrical power simply by saying that the amount of joule that you have when you take meter and a second as basic quantities defines then, with this value of the Planck constant, defines you a kilogram unit. Yeah? So it's now a derived quantity, and you can realize this experimentally, for instance, by a watt balance, where you have a body moving through moving a coil through a magnetic field, and thereby generating an electric current, which then with quantum mechanical devices like Josephson junction, you can relate to the Planck constant. So now we can measure actually the kilogram. Now when we go to subatomic physics, of course we need different concepts. So of course we have special relativity, and you know that mass is just a different form of energy. And if we go to the standard model we are interested in, then mass is basically notion of mass is basically coupling strength to the Higgs boson. So we are basically, if we talk about masses, then we basically are interested in coupling strength of particles among each other. Huh? And so when we ask a question now, for instance, what is the value of the heaviest particle in the standard model, is the top quark mass. So when we ask this, what is the value, then we have to apply principles of quantum field theory in order to answer this question. And quantum field theory basically tells us we have to apply certain procedures in order to extract, first of all, a meaningful definition. Yeah? So here, for instance, if we start off with QCD, in gauge theory of the strong interactions, we have a simple Lagrangian at the classical level. As is given here, it is the field strength squared. So F mu is the field strength that describes the dynamics of all gluons in the theory. And then we basically have a Dirac term here. We have a quark, an anti-quark, a covariant derivative, and a quark, plus or minus a mass term here. And this is giving us the dynamics of all the quarks in the theory. So we have the gauge fields and the matter fields. We have a covariant derivative, where we couple basically the partial derivative in a gauge invariant way via 1 power of the field strength to the gauge field. And this is it, and it contains a couple of, at this level, formal parameters, which is basically the strong coupling, alpha s, which is gs squared divided by 4 pi, and the quark masses. So these are formal parameters, and we have, if we want to measure them or if we want to determine them, we have to give them some meaning. Because once we quantize the theory and we consider radiative corrections, we have to renormalize the theory. We have to carry out a procedure called renormalization, which basically means we have to fix the quantities in a specific scheme by making certain subtractions from ultraviolet singularities. And then once we have done this, then the challenge is that we are facing is we have to look for suitable observables which we can measure first of all, and which we can describe in theory, such that the theoretical description carries a certain dependence of the parameters that we are interested in, so that we can compare data and theory and thereby then extract this quantity. And the classic example, at least in QCD, for this procedure is the coupling constant, the coupling constant renormalization. Because you're basically asking what's the strength of a quark interacting with a gluon, and this is similar question as if you ask yourself in electrodynamics, you have an electron and you ask yourself what's the strength of the interaction of the electron with a photon. And then when you quantize the theory, then what you're basically having is you're having here such Feynman diagrams at the one loop level. You have here a quark coming in, and this interacts with a gluon, and there is another exchange of a gluon over here, or you have a quark coming in here, there is a gluon being exchanged, and then the gluon splits up into a vacuum bubble of quark-antiquark pair, which annihilate again, and then out comes the gluon. And these are precisely the same diagrams you would have in quantum electrodynamics for the interaction of a photon with an electron. If you calculate them and you calculate the effect of those, you need to evaluate Feynman diagrams, and they give you the prescription of how the electric charge, or in the case of QCD, how the strong charge changes as you change the scale. And if you do this in electrodynamics, then you will discover that those diagrams give you basically the effect of the screening of an electric charge. As you go closer and closer, you see that the electric charge is green. Now, when you go to the theory of the strong interaction, you have also a particular feature of the gauge theory being an SU3 gauge theory, namely you have a self-interaction of the gluons among each other. So you have additional diagrams, because you can have a gluon splitting up in a gluon pair, and then those two gluons coupled to the quark here. And they give you the effect of anti-screening of the colored charge at small distances, and this is giving rise to the feature of asymptotic freedom in QCD. So you can code this up in what is called the QCD beta function. This gives you the scale dependence of the strong interaction as you change the scale. So this is sometimes also called the running of the coupling. So you have alpha s now becomes, after quantization, it becomes a scale dependent quantity. Depends on the scale mu, basically where you probe it, if this is at high scales or low scales. and equivalently it could be at short distances or long distances. Yeah? And this is determined by a quantity called a beta function. You can calculate it, and this beta function has a negative sign. So that basically tells you, as you go to higher scales, you find this picture which is shown in this plot here. So on the horizontal axis we have mu, the scale. We increase the scale mu, and we see the coupling goes down. Yeah? And it basically means that as you go to smaller and smaller distances, the coupling vanishes, and asymptotically quarks and gluons become freely interacting particles. So we believe our hadronic matter around us is being made up of quarks and gluons. Yeah? So we can't see any quarks and gluons at our scales, which is long distance scales, which is where the coupling basically becomes very strong, so they are strongly bound. But if we're able to look inside the proton at very short distances, then they should behave almost as free particles, because the coupling vanishes asymptotically. No? Now, if we want to carry out the same procedure for the mass of a particle, for the mass of a quark in particular, then we also have to consider radiative corrections. So we have to consider, we start off with a quark, which is a free quark propagator here, the type of thing that you derive from the Dirac equation. And then you have one loop corrections, two loop corrections, and if I write it in a way like this, then you can basically resum this to all orders. These so-called self-energy corrections, capital sigma here, and you see that this is basically the start of a geometric series, which you can then resum in a way that instead of the free quark propagator, which would just be I over p slash minus mq, you have now the resummed quark propagator I over p slash minus mq minus the self-energy. And this is just a formal resummation. If you want to make sense of it, you have to again compute quantum corrections. So you can ask yourself, what is the one loop correction to a heavy quark mass? And this is a simple one loop diagram like this here. You take a heavy quark, you exchange a gluon, and you absorb it again. So this is a quantum effect here. And then you can sit down and calculate it. And as I said before, we do have, when we do this, the integration over all possible loop momenta that this gluon has here, then we basically integrate from very low scales to very high scales. And we're encountering ultraviolet divergences, which we need to regularize. So you can simply, could say, okay, I take an ultraviolet cutoff, capital lambda for instance, and just calculate up to this scale. This is something you can still do at the one loop level, but if you want to go to higher orders, then what is a better way to regularize is to analytically continue the number of space-time dimensions from 4, which we're living in, 3 space and 1 time dimension, to d, by shifting it a little bit away from 4. So we like to do these calculations in d dimensions, which is 4 minus 2 epsilon dimensions, and then we can actually calculate this, and our ultraviolet divergences manifest in terms of our simple poles in 1 over epsilon. Yes, please.
You mentioned heavy quarks as energy. Well, that's true for lighter quarks as well, right?
For lighter quarks as well. So basically the same formula that I've written down here is exactly valid for light quarks. It's just you eliminate the mass everywhere. Huh? And now then, if you do this for light quarks, then just the first term would survive here, and you have to make sense of it. For heavy quarks, also the second term here survives, and you have to treat them differently in the renormalization prescription. Basically, the first term, the first infinity here, you can fix by performing what is called a wave function renormalization, and the second term you have to fix by saying, okay, what is now the prescription? How do I define my mass? Because I said initially when we were talking about the QCD Lagrangian, we start off with some formal parameters, and now I have to say, how do I actually fix these quantities? And I have to relate my bare mass to a so-called renormalized mass by simply subtracting a given amount of some ultraviolet divergence, which would be the 1 over epsilon pole, plus possibly more. So this is not a unique procedure. And pictorially it is described here by expressing the self-energy correction here. When you expand it in terms of the free propagator, then the one loop diagram, and then something called a counter term, where you basically remove for instance, these infinities here. And now it's up to you. It's up to you to make a choice how you want to do this. Yeah, and whatever choice you make has then some consequences for the parameter and also for the behavior. And so the choices that are typically being made are inspired by some physics ideas. So the first idea is basically to do the subtraction in a way that you absorb all the self-energy corrections here in a way that that when you put the momentum on shell, yeah, so when you demand that p slash is equal or p is equal to the mass of the quark, that you will recover here the pole of the propagator. Yeah? And this is then called, such a prescription is then called a pole mass, yeah, or on-shell mass. You can do this. It makes sense in theories like quantum electrodynamics, where you have electrons, yeah, and the electron is an asymptotic state at infinity. Yeah? So then it makes sense, and you can really, you can think of an electron as an asymptotically free particle. In a strongly interacting theory, where you have quarks and gluons bound in hadrons, yeah, you have no asymptotically free quark. So this is why such a definition, although it is being used in practice a lot, is physically problematic, and it also comes with a couple of disadvantages, namely that there is then an intrinsic limitation in the precision with which you can define this quantity, related to what is called infrared renormalons. Yeah? So there is basically a problem with the pole mass, because it's not really physically well motivated in QCD. What you can do instead is you can do what you have also done for the strong coupling. You basically just remove the leading singularities, the leading ultraviolet singularities. This is called a minimal subtraction, and then you are in a so-called MS, minimal subtraction scheme, or MS bar scheme, if you also subtract a couple of constants which always appear, like gamma Euler and the log of 4 pi. Yeah? And then when you do this, you basically have to find a scale at which you do the subtraction, and in this way the mass suddenly becomes scale dependent as the coupling was. Yeah? So I had shown you the plot for the running coupling before, and now we see we also get scale dependent masses in the theory by doing renormalization, where we define just the mass through the minimal, so through the MS bar scheme. Yeah? And you can also calculate this running then of the mass. So this is for the top quark shown here. So basically you start from a top quark as a function of the scale mu. We have, say, 163 GeV up here, and then you run the scale of the top quark down to, say, 90 GeV at the 1 loop level, 2 loop level, 3 loop level, 4 loop level. And you see that basically the top quark becomes lighter as you go to lower scales by a few percent. Yeah? So then when you measure the top quark in that scheme at the given scale, you also have to define the scale at which you're doing this. Yeah? Of course, we can do as we like in theory, and you can also relate your calculation done in one scheme to the other in a finite way. So for instance, if you have something calculated in terms of a pole mass, you can translate it in terms of something, an expression as a function of the MS bar running mass, just in a perturbative expansion. It's just not that this transformation is always converging very well, especially for lighter heavy quarks like charm or bottom. Yeah? Okay, so where do we get all this information about the particles? Well, this is the LHC, you probably know. It's the largest, highest energy collider operated at present in Geneva. So here is Lake Geneva, Geneva Airport. Here is CERN, and here you have the pre-accelerator, and here you have the large LHC ring with 4 experiments. The 2 main ones, Atlas and CMS, are doing the physics we are interested in. So there you can look at the data, you can ask the experimentalist, so what's the value that you've measured? And so for the top quark, we can basically look it up. We open our social media account, for instance, go to Twitter, and then on Twitter we find the top quark mass measurement combined from Atlas, CDF, D0, and so on and so forth is 173.34 GeV with an incredibly small uncertainty. Yeah? And so at CERN they were so proud that they even published it on Twitter, but they forgot to mention which scheme it was. So it's a problem, because they also don't know which scheme it was. So this is just an advice that you shouldn't believe anything which is posted on social media. Instead, it's better to go to the research papers. So the experiments are also measuring the mass in a well-defined scheme. So this is just from a CMS collaboration which appeared earlier this week, CMS publication which appeared earlier this week. So they're measuring, for instance, the pole mass at the one loop level from measuring TT bar plus 1 jet samples, and they derive a value of 172.94 GeV with an error of, say, plus minus 1.3 GeV. Yeah? So this is then some number which is credible. Yeah? Now, why do we care? Or what can we do with such a number? Well, we can, as we're interested in features of the standard model, we can take this number and look at implications of that number for the rest of the standard model. In particular, we can look at the implications on the electroweak vacuum. And in order to understand that, we have to basically switch from QCD to the Higgs sector, and we have to look how is the Higgs interacting with the rest of the particles. And here you have the Higgs is a scalar particle, so its dynamics are basically being described by a Klein-Gordon equation, but it moves in a potential, and the potential for the Higgs is basically this quartic potential here. So you have phi dagger phi minus the vacuum expectation value squared, and this is giving you this typical Mexican head potential as a function of the Higgs field, and there is some coupling lambda, which is determining the self-interaction strength of the Higgs field. So the Higgs can also interact with itself. So the way it does this, for instance, if you have two Higgses being scattered, which we can only do in theory, there is no collider where we can do this, but we can write down all the diagrams and calculate this. Then to leading order, we just have the four Higgses here. And then if we look at higher order corrections, we have like self-energy corrections in the S channel, in the T channel, in the U channel. We can basically calculate them. So this is how the Higgs interacts with itself. But the Higgs also interacts with all the other particles in the standard model because it gives mass to those particles via its coupling strength, and these are the so-called Yukawa couplings to the fermion matter, for instance. So the Higgs can interact with a top quark, for instance, through such a box diagram here. So two Higgses, and then you have a top quark box, and two Higgses come out. You can have gauge bosons in a loop, or you can have Higgs self-interactions. So you can calculate, like we have done before, for the strong coupling, you can calculate those loop diagrams, and you can see how is the scale dependence now of the Higgs self-coupling. And this gives you a renormalization group equation again for the self-coupling of the Higgs field, which I've written down here to the one loop order. So the self-coupling of the Higgs changes with the scale Q. Q is any large scale, and it changes with the Q, and on the right hand side basically see it starts off with 24 lambda squared, and in terms proportional to lambda and some constants here. And in order to understand broad properties of this equation, you can basically look at two limits of this equation. You can look at the limit of large masses, large Higgs masses, which imply that the self-coupling is very large. And so if you look at this particular limit, then from all these terms on the right-hand side, you just keep the largest one, which is proportional to lambda to the squared, and you neglect the other ones, and you can basically solve this differential equation in a simple way. So what you then get for the self-coupling as a function of the scale is on the right-hand side something proportional to the Higgs mass, and then you have a denominator which is 2 times the vacuum expectation value minus some constants times the Higgs mass squared times the log of the scale Q normalized by the vacuum expectation value. Now, this equation tells you that as you increase the scale, the self-coupling rises, But there is a certain scale where you basically hit a singularity here in the denominator. And this singularity is called a Landau pole. Yeah? And this is giving you, the Landau pole is giving you an idea about the largest scale where suddenly this equation breaks down because you're hitting a singularity. Now, if this equation becomes singular, then it basically means that your theoretical description is not applicable anymore. Yeah? And now you can ask yourself the question, what is the largest scale at which I have to cut off with a capital lambda here, up to which I can trust my theory? Yeah? And so you can basically, from looking at, from solving here for the pole of this denominator, you can basically determine a condition for this cutoff in terms of the Higgs mass and the vacuum expectation value. So your cutoff lambda has to be smaller than or equal than the vacuum expectation value of the Higgs field times the exponent of the vacuum expectation value squared divided by the Higgs mass squared times a few constants. Huh? And if we are able to shift this cutoff all the way to infinity, then our theory becomes trivial, because then basically that means there is a vanishing self-coupling, so there is no interaction anymore. Huh? In practice, we're not interested in pushing the scale all the way up to infinity, but we would already be happy in pushing the scales up to the Planck scale, where we know that our normal particle physics interactions don't really describe the whole world anymore, because the gravitational coupling also becomes of equal strength, and so we would also have to include it. Yeah? So the Planck scale for all our purposes in particle physics is fine, which is already pretty large, so it's 10 to the 19 GeV, but we would be happy to shift it to this. The other limit in which we can analyze the equation for the running self-coupling of the Higgs field is when we look at the opposite limit. This is the small mass limit. And in the small mass limit, from the right-hand side of our equation here, we just keep the constant term here, because lambda and lambda squared are smaller, so the constant term is the leading term. And here in the small mass limit, this is now given by the largest Yukawa coupling, and this is precisely the coupling to the top quarks. So here the top quark mass enters, and we can again solve this differential equation in an exact way. And then we see that as a solution we get something where the self-coupling of the Higgs field starts off from some value lambda naught, and then it decreases. Because this term here is negative, so it decreases, and it can take any arbitrary negative value. In particular, the self-coupling can become smaller than 0. Now, when the self-coupling becomes smaller than 0, this is again a problem for the theory, because then our theory formulation with the potential of the Higgs field doesn't make sense anymore. So self-coupling positive means we have a positive potential. If suddenly the self-coupling is negative, means the potential is upside down, so something is not working anymore. So we would like to have this lambda strictly positive, and this again defines us a certain condition for the validity here. Yeah? We can again ask ourselves, what is the cutoff on the highest possible scale, so that our self-coupling is not yet negative. Yeah? This again gives us a cutoff, lambda. And this is the condition on the so-called vacuum stability of our electroweak vacuum, so that the cutoff should be smaller than the VEF times the exponent of the Higgs mass divided by the top Yukawa coupling to the fourth times the vacuum expectation value squared. Yeah? Now, you can again ask yourself, how large can I make this scale, so that the Higgs coupling is still positive, so not becoming negative, and how does it relate with the other quantities that we've measured? And you can basically express those two conditions, the triviality bound and the bound for vacuum stability. You can express this, including higher orders, in a positivity condition for the Higgs boson mass, which involves the other parameters, namely the strong coupling alpha S and the top quark mass. And you can ask yourself, can I push the cutoff on the theory all the way to the Planck scale, demanding I still have a well-defined theory, meaning I have a positive definite electroweak vacuum potential, and what does it imply on the Higgs mass? And people have done this, including not just leading order, as we have discussed this now, but also next to leading order and next to leading order corrections. And this is the result of the analysis. If you require vacuum stability at the Planck scale, given as an input the top quark mass and alpha s, and what is the bound on the Higgs mass. And this is given in the equation up here. So basically, if you require this, then the Higgs mass has to be heavier than 129.6 GeV times an additional correction coming from the pole mass of the top, minus a predefined measured value, and another correction dependent on the value of the strong coupling constant offset from a predefined value, plus some other theory uncertainties. A better illustration maybe of what we are seeing here. Then depending on where you are with the top quark mass and the Higgs mass, you're either sitting in regions where the electroweak vacuum is stable, so this is where the self-coupling is positive, this is the green area here, or you're sitting in a region where the electroweak vacuum is metastable. That means your self-coupling or your Higgs potential doesn't have a global minimum anymore, but it has developed another minimum further away, but there is a potential barrier, but tunneling through this potential barrier would take longer than the age of our universe, and so then we are safe. Or you can go here to the unstable region, which is red up here. This would be a region where you basically immediately decay. Now you can see we have analyzed this and extracted the value of the top quark mass. From top quark data, we got something of the order of 170.5 GeV for the pole mass. So we would claim standard model is in good shape all the way up to the Planck scale. And we are sitting here at the boundary of the region between stability and metastability. If you take the number that the CMS experiment has measured earlier this week, they came up with 172.9 GeV. They would be sitting up here, also with an error, so they're sitting in a metastable region. And currently, the uncertainties that we have on the top quark mass and also on the other parameters which we need in order to make such a precision analysis are not precise enough so that we can really decide on where we are. But it's a very interesting question, and it basically decides eventually on the fate of our universe. I mean, given that we have the standard model, are we happy with the standard model, and are we happy up to all possible scales, or is there a compelling need for new physics even at lower scales, which we could see from such an analysis. If our parameters would bring us up here, then we would definitely know that there must be new physics before the Planck scale. Right, so this is why we're interested in these quantities, and in order to do such precision analysis, we have to work hard on a number of topics. Basically, we have to provide the experimentalists with predictions they can compare to their data, from which we can then read off these parameters. So if we want to take the top quark mass, for instance, from a cross-section, then we have to calculate this process over here. So two protons scatter, you pull out a parton out of each proton, and they undergo a hard interaction here. You produce, say, X is a top quark pair, and some other final state. This is the master formula here. The two parton densities for the dynamics of the partons inside the quarks and the gluons inside the proton, and the hard partonic cross-section, which you need to calculate also to higher orders. And then once you have done this, you can basically look at your formula, and you can basically try to see what's the sensitivity of my theory result to, say, the mass parameter. So you can look at changes in your cross-section compared to changes in the mass, and this gives you sensitivity. And the higher the sensitivity is, the better such an observable is suitable for extracting a parameter like the mass. So if you look at the top quark total cross-section, then this is basically giving you a factor of 5, which is already okay. So you can basically do something. And so we do have exact results to next to leading order in QCD available. for this process here. So as a function of the pole mass, we have here leading order. So this is for LHC running at ATV, for example. We have the leading order prediction, the next to leading order prediction, and then the red line is the next to leading order prediction. So you see that the higher you go in perturbation theory, the larger your cross-section becomes. But the good thing is that this expansion is apparently converging, so the successive increase due to higher orders becomes smaller. And then you can basically look at what the experimentalists here have measured in terms of picobarn here, say, on the right-hand side, and you can take this and you can read off a mass value here. Yeah? The other thing to judge the quality of our approximation is if we now vary the factorization and renormalization scales involved, we also see that the scale dependence, if we vary it by a factor of, say, 2 or 4 left and right relative to the pole mass of the top quark, we see that at leading order we still have a big scale uncertainty that becomes smaller at next to leading order, and it becomes flatter at next to leading order. So the flatter the scale dependence, the better and more stable our theory prediction is. So this is for the pole mass. We can also do the other mass definition that we have discussed. So we can take the running mass. You can basically see in comparing the two pictures, so left is the pole mass, right is the running mass, that here the convergence of the perturbative expansion is even better. Yeah? So you basically see that going from leading order to next to leading order to next to leading order, the things can converge even faster, which is then giving you even more trust in what you're doing. Yeah? So that you're really capturing the essence of the quantum corrections. You can also compare the scale dependence between the pole mass and the running mass definition, and then you can also see that even the scale dependence of a cross-section with a running mass definition is much improved here. It's even flatter. No? Now, this is the type of predictions we can take, and there we can read off the top quark mass, and then we can take it to the experiment. But in order to do that, we also have to worry about the other parameters which enter the game here. Yeah? I mean, after all, if we look back at our master formula, then the heavy quark mass is just one parameter. We also have explicit dependence on the strong coupling constant, and we do have explicit dependence on the parton luminosity here. Yeah? Because after all, somebody also has to tell us what is the momentum density distribution of the partons inside the proton. How do we get this? Yeah? This is also some quantity which we have to extract from the experiment. Yeah? And we also have to make progress there. Yeah? So the inner part, this is the hard scattering cross-section, which if we calculate it to, say, NNLO, as I've shown before for the case of top quark production, then we typically, as a rule of thumb, can reduce the uncertainties we have due to scale variation to less than 10%. In the case of top quark production, we're even a bit better. We're at the level of 5%. But we also have to worry about the other part. So basically, what's the parton composition of the proton? The things that we're used to that we use to collide upon each other. Huh? Because there are no free quarks and gluons at the LHC. So we have to be able to make also statements about these quantities, which is also not an easy problem. And since all these quantities are related, they're correlated with each other. Whatever I take for the PDFs as input, or whatever I take for alpha S as input, will also have an effect on the top quark mass that I extract. So it's basically a multi-parameter problem. I cannot just try to extract one parameter. Huh? Now regarding the parton distributions inside the proton, we have to fit them from data. This is a strong interacting problem now at large distances. So we cannot really calculate it. We can hope that lattice QCD at some point will make some progress there. But at the moment we have to fit it to data by taking different sets of data measured at different scales and relating it to each other, because we can make statements about the scale dependence of the PDFs. And this is governed by another renormalization group equation. So the scale dependence of the momentum distributions of the partons inside the proton is just a renormalization group equation where we have a kernel kernel are so-called splitting functions here, convoluted again with the Parton distributions. And they, as a physics picture, what they describe to us is how do you resolve quarks and gluons inside the proton. So if you, for instance, look with a photon inside a proton, and the photon has a certain long wavelength, then you just see a gray ball. But if your photon becomes of shorter wavelength and shorter wavelength, then suddenly you start to resolve quarks and gluons inside the proton, characterized by such splitting. So you basically have the splitting of a quark into another quark and a gluon, and the quark carries a momentum fraction x of the original quark momentum, and you can have splittings of gluons into two quarks or gluons into gluons. And so you have to look at all possible combinations and calculate those, and this determines you this kernel of the evolution equations, the so-called splitting functions. And we can again do this in perturbation theory up to very high orders. So currently the first three terms in this approximation are known, and the fourth term is under active investigation. So we also try to get more information there. Physically, what this evolution equation does to you is you basically have, as a function of x, you have, say, valence quarks in a proton, you have C quarks in a proton, you have the gluon in a proton, and this is their momentum distribution at low scales, say q squared of the order of 15 GeV, in a range between 1 and 10 to the minus 2. So basically for the valence quarks here, you see this little bump here at peaking at around 1/3, and this is basically just a bump that you get from the old Feynman idea that you have three partons in the proton, and they share equally the momentum fraction, the momentum of the in equal fractions. They share the proton momentum, and this would peak here at 1/3. But in reality, it's of course a bit more involved. So you get distributions like this here, and they depend on the scale. So if we now run our renormalization group equation, go up to high scales, then we see the gluon distribution is rising, the valence quark distribution is shifted a little bit, the C quark distribution is also rising. So we see how these quantities change. And we need to get precise input, because at the LHC, what we have is, when we're interested in top quark production, we're sitting at scales, say, of the order of top quark pairs. We're sitting at scales of the order of 300 to 400 GeV. This is over here on the vertical axis. And that means we're sensitive to parton kinematics in a range between, say, 1 and roughly 10 to the minus 3. If we see the top quark somewhere in the main detector between rapidities minus 2 and 2 here. So this would be this region here. And the data we have available in order to determine the parton distribution comes, for instance, from the Hera collider in the past. This has been collected in deep elastic scattering experiments. So we fit some parton distributions at those scales here, and then we have to evolve them with a renormalization group equation up to high scales, and that has to be precise enough. So this is also why we're interested in understanding that part to good precision. And the calculation of such splitting functions, or if you wish, anomalous dimensions of certain operator matrix elements, proceeds in a way, in a standard way. So you have the splitting functions, you can take the Mellin moments, and you basically get in Mellin n space some anomalous dimensions, which define the renormalization behavior of operators like this here. So this would be a typical quark operator. You have an anti-quark field, you have a gamma mu, you have a number of covariant derivatives hitting another quark field here, and then you look at the loop corrections to such an object. So a typical Feynman diagram would be like this here. You have a quark coming in, you have a number of loops, quantum corrections here, here is the operator, and you go out with a quark again. So you're basically computing matrix elements of this quark operator between external quark states, which is a two-point function problem. It's just due to the operator, it's a bit more complicated than the examples I have discussed before. But again, the textbook calculation is not so difficult. So you just have these three diagrams here. You can take an incoming quark, you exchange a gluon. Here's your operator insertion. You can also pull out a quark of the gluon out of the operator, and then you attach this gluon, say, to this quark line or the other quark line. So this comes with a factor of 2 here, or you have some self-energy correction here on the external x. Yeah? You basically calculate then this 2-point function here. You have your momentum flow in this way. Again, you have to renormalize, you have to regularize the in-dimensional regularization because there are ultraviolet divergences here. So then from the pole part, 1 over epsilon, from the ultraviolet divergence, you can read off the coefficient of this pole is basically the anomalous dimension. And if you calculate this, so this is a textbook example here, then for this operator you find something which is very nice and interesting. So you find the color coefficient. This is the Casimir of the fundamental representation, since we're looking at quarks. So it's 4 over 3 in QCD, and then you have some functions depending on the number of covariant derivatives which you have sticked into your operator. So n, we like to keep n symbolic. And then you have a function S1 of n, and this function S1 of n turns out to be a harmonic number. So you start to see also some interesting mathematics here. This is basically the beginning of also an interesting thread in mathematics, because if you want to do this kind of computation systematically to higher orders, then you see that starting out from now harmonic numbers, which have been studied already by Euler 250 years ago roughly, you build up a particular class of functions, so-called harmonic sums, by just simply iterating the summation structure that you have here. So harmonic numbers are just the numbers you sum over all inverse powers 1 over I. You sum them from I equal 1 to n. This is giving you the harmonic number. Now, what you can do is you can basically take powers of I here, so you can sum over 1 over I squared, 1 over I cubed, 1 over I to the 5th, and so on and so forth. This is then giving you Riemann zeta values, for example. So values of the Riemann zeta function at integer values. But you can also iterate this definition here by taking another sum outside. So this is giving you then a recursive definition of so-called harmonic sums. So just you have a harmonic sum with indices m2 to mk of argument I, and you just sum over it again from I equal 1 to n, and you can weight this sum by, say, plus or minus 1 power to the 1 to the power I, and you can you normalize by I to the power m1. Yeah? And so this is what give you then the next weight harmonic sum. Yeah? The depth is higher and the weight is higher. So the weight of a harmonic sum you can basically define by taking the absolute value squared of all these indices. This is giving you a certain weight here. Now these are interesting functions. They have a very rich mathematical structure. We get them, for example, by working in dimensional regularization. So when we expand gamma functions, which we get by working in dimensional regularization, then we see expanding these gamma functions around some integer number in epsilon. Those harmonic sums naturally appear here. But they also have a rich mathematical structure. So just to give you one idea, if you multiply two harmonic sums of the same argument, so same n but different weight, then you get out a sum of single harmonic sums again. Yeah? And the algebra behind this has a so-called Hopf algebra. So there is some interesting mathematics behind this. You can use this in order to perform certain manipulations with the objects that you get, and it helps you to simplify to first of all do your calculations and also to simplify the results afterwards. So now if we want to push further, I told you that basically we're interested we're basically interested in getting here the next term in our evolution equation for the partons. Then the 3-loop level has been done. We now have to work at the 4-loop level, and this is some calculation which we are not doing by hand anymore, but you basically have to set up the computation such that you can do it by computer. So first of all, there are way too many Feynman diagrams to draw them by hand, so you generate them automatically by computer. then you also don't want to do the calculations individually, so you try to set up an algorithm such that you can parametrically reduce all the Feynman diagrams to a given basis of so-called master integrals, and you can do this with algebraic relations that you derive by exploiting integration by parts identities for such Feynman integrals. And then you basically need a powerful symbolic manipulation program for doing computer algebra, because the expressions will be very large. So known computer algebra systems like Maple or Mathematica will not be able to do the job because the expression size is simply too large. So in order to run these equations, to run such computations, we like to use Form, which is a program written by Jos van Maaseren. And then you also need some ordering principles. So for instance, you need to order all your diagrams, first of all in terms of color factor, which is trivial, but also in terms of topology, which helps you to set up such a reduction algorithm. Yeah, and then at the for loop level, so for the diagrams, for this quark anomalous dimension that we're interested in, you then group all diagrams together, and then in terms of meta diagrams, you see that from 1 loop, 2 loop, 3 loop, 4 loop level, you go from 1 to 7 to 3 to 650 so-called meta diagrams. Huh? So just to give you an idea, this is then the list of basic topologies. So these are the ones that to which we have to reduce in the end all our diagrams. So you see that you of course have simple topologies like the concatenation of just one loop integrals, which you can simply do, but you also have very complicated non-planar integrals up here, which you also have to compute. Yeah? And now what can be done with current technology at the for loop level? You can compute a number of fixed Mellin moments, so you have to fix this Mellin into an integer value, so 2, 4, 6, or you can, for the quark case, you can also take odd ones, and then run the parametric reduction. So you cannot run it at the moment for arbitrary n, and then simply run it. And what is computationally feasible is you can do the full calculation up to, say, n equal 18. Sometimes you go up to 19 or 20. And if you have easy topologies, you can go up to n equal 80. Yeah? But this is really the computational limit. So when you want to evaluate this non-singlet anomalous dimension at Mellin n equal to 18, you're talking about 150,000 CPU hours. This would be like 200 days in real time on a single core server, but you have to distribute it, of course, but we are still talking sizable fraction of a year also on a decent sized cluster. Yeah? And the other problem is the size of the intermediate expressions. So when you go for easier topologies up to n equal 80, then you can see, I measured this for a moment, n equals 73, that you're having expressions of the order of 20 terabyte, which you also need to store on disk space somewhere. Yeah? And so this would basically, if you were to use Maple or Mathematica with such a problem, then it would basically blow you out of the computer. It wouldn't fit into the RAM of your computer. Yeah? So you basically have to run this on some servers which have enough local disk space, but also sufficient RAM. Yeah? And then once you've calculated the number of fixed Mellin moments, then the fun part starts, because now you can ask yourself the question, do we know enough about the mathematical structure of our answer so that from a given finite set of Mellin moments, we can actually reconstruct the full answer? And this is possible in some cases. Basically by solving then a system of Diophantine equations. And for that we have to go back, we have to look at how many different possibilities, how many different harmonic sums can we have. So at the for loop level, we're basically talking harmonic sums up to weight 7, and there are 2 times 3 to the power 7 minus 1 sums at weight 7, so 3 to the 6 times 2 is a large number, and if we have only 18 moments, then it doesn't look so good. However, we know something about the function that we are calculating because it has been researched, so we know a little bit about its analytic properties as a function of all n. So it should obey certain reciprocity relations, which is basically giving us an idea on its analytic behavior as a function of n, which then constrains the possible harmonic sums that we can have here. Then Of course, there can be additional denominators, but also those can be limited in structure. And so if we do our math, then we would be basically counting 255 objects at weight 7. This is still too large if we have only 18 moments available. However, we can go into the large NC limit, which basically reduces us to planar topologies, and it also eliminates all harmonic sums which have a negative index here somewhere. And this greatly simplifies the problem, because then we do the counting and we see that weight W sum, reciprocity respecting sums are given just by the Fibonacci numbers. And so if we include additional powers 1 over n plus 1, then we basically have a total number of unknowns, Fibonacci number of weight plus 4 minus 2, and at weight 7 this is 87. So we have 87 unknowns, we have 18 moments, but we also have a number of constraints, because we know in addition certain features that we would like to see at the large and small x limit, so when n goes to infinity and when n goes to 0, and that adds up to 46 constraints in total. So now we're having 87 unknowns, 46 constraints, and we have 18 moments to fix. To fit, and this is a good ratio that we can successfully then try applying this approach of solving Diophantine equations with a nice algorithm devised a few decades ago by mathematicians Lovac, Lenstra, and Lenstra, and that actually helps us. With that we succeed to find an analytic solution then. So in view of time, let me just sketch to you the analytic solution here that we found for the non-singlet anomalous dimension as a function of n here. So this is now for different number of quark flavors, NF3, NF4, NF5, and NF6. So you see the red line is the large NC result, which we know analytically, and then the blue dots are the full QCD fixed moment calculations, which go here up to n equal 18 roughly. And you see that the large NC approximation is already doing quite well. We can also, with having an analytic solution, we can go invert the Mellin transform, go back to X space, and then finally with a splitting function stick this into our evolution kernel. So we can now look at how stable or how precise can we predict the parton evolution as we vary the scale again. And here again, as a function of this, the ratio of the renormalization over the factorization scale, we see that going from next to leading order, next to leading order, now going to n cubed leading order, with these for loop results, we basically have pretty flat scale dependence everywhere, which is a sign of a high quality theoretical prediction. Right. So last outlook here is where do we get information about the analytic behavior that we are expecting in our QCD results? And there is an interesting relation between QCD and other gauge theories which have extended supersymmetry, in particular n equal 4 super Young-Mills theory, where you can consider also correlation matrix elements of correlation functions of different operators, and you can basically also look at their spectrum of scaling dimensions. So they also have an anomalous dimension. And in such a theory like n equal 4 super Young-Mills theory, people have been able to actually solve the anomalous dimension that we are seeing here for all values of the coupling by mapping the problem to some integrable model. Some Heisenberg spin chain, for which with the beta ansatz people were able to derive an all-order solution. And then re-expand this and comparing to fixed orders. And what we are seeing here is that there is basically a one-way correspondence between QCD and n equal 4 super Young-Mills theory, because we can trivially set all our color factors in QCD, identifying quark and gluon color factors such that we mimic a supersymmetric particle content of our theory, identifying them, and then just keeping the leading transcendentality part of our harmonic sums and zeta functions. So for instance, looking at the anomalous dimensions at leading order of the quarks or the gluons, identifying the color factors and keeping the leading transcendentality part, which would be the 4 times this harmonic number here. We see that first of all, there is something like a universal anomalous dimension as predicted by n = 4 super Young-Mills theory, and it also matches precisely what people get in this theory. So in n = 4 super Young-Mills theory, people have, apart from this integrable model, they have also applied constructive approaches to expand this beyond the large NC limit to 4 loops, 5 loops, 6 loops, 7 loops, and so on and so forth. So we also have some more insight there, which we can basically use, or let us use as inspiration to see what kind of things we do expect from such calculations in QCD. Okay, so just to finish, so these are the mathematical problems that are concerning us. The other question is there, beyond the LHC, is there some bright future, some outlook that motivates us on the theory side to do these experimental computations? And I think yes, there is, because there are now plans for a new collider to be built at Brookhaven, which is an electron-ion collider, which is colliding an electron beam and then colliding the electrons on protons and or deuterons, lighter nuclei, and this is certainly a machine. Given the size of the accelerator, this will certainly be a machine where again these aspects of strong interaction physics that we just discussed will be very important and should become operational around 2029, so in roughly 7 to 8 years. And given the expected precision of the experiments then, you can be sure that there will be high demand for further precision predictions in QCD. Thank you very much.
Thank you, Professor Moch, for this very fascinating talk about the precision physics in standard model and particle physics. So now the session is open for questions. So if you have questions, please feel free to ask.
I have a question about the Mellin moments.
Yes.
Now, if you don't transform to Mellin space and then have to invert it back, you don't have to worry about these identities. How hard is it to just directly do the X-space integrations?
So it is also possible. It requires it requires a different algorithmic setup. It requires a different algorithmic setup. So when the basic added complication is that when you look at integrals like this here and you have additional x dependence, then you're basically you're not just computing 2-point functions, but there is some additional scale attached to it. So basically you're increasing the complexity to something like a 3-point function, which is more difficult. And then the whole reduction procedure, trying to simplify all these Feynman integrals with integration by parts relations, this becomes much more involved. So basically, instead of having to solve simple 2-point functions, you would have to solve roughly things which correspond to 3-point kinematics with an additional scale, and then you would have to solve associated differential equations, which is simply harder. So this part hasn't been done yet. I think in the future, I would expect also some developments there. It's simply beyond what we can do at the moment. Yeah. So I've had a PhD student, he was basically able to now implement this at the 3-loop level, yeah, completely, doing such a computation in X space, but we are not yet at the level that we can do this at the 4-loop level. Yeah.
But if you are able to do it, will it be faster, the computation?
So yes, that should be much faster, because at the moment what we are basically, so if you look at numbers like this here, what is basically limiting you is each time you add a Mellin moment, you have higher powers of denominators to reduce, the expression size grows. So in that sense, if you can do an X-based computation, it should be definitely more efficient at the computational level. So we should not be seeing this increased size in computing time, and we should also see smaller needs for disk space. Yeah? But the development steps to reach this is the more difficult.
You mentioned about top quark mass. I mean, there are many definitions for top mass, actually. Which is the kind of one that is extracted from the experiment, actually? Because you mentioned in the beginning.
Yeah. So basically, right. So basically, when the experiment started off, when the experiment started off with the number they have quoted here, you know, they were just they were measuring the top quark final, the decay products of the top quark in the final state, and then they were comparing this to Monte Carlo samples and simply computing the kinematics. But this required the use of some Monte Carlo program, and there you basically have you simply have part-on shower modeling involved, and this is why there is not really a well-defined scheme prescription here. And once they have realized this, now they try to, of course they need to use Monte Carlos, but they try to use to eliminate the dependence on whatever mass value they put in a Monte Carlo. They try to eliminate this from the measurement and instead really work with observables like total cross-sections or differential cross-sections, for which they have fixed order predictions like to NLO or NNLO. And then what they're typically using is the pole mass or the running mass. So these are then the masses which they use which they extract from such a procedure, and then they try to also check for internal consistency, for instance. Yeah? Like,
This was not the pole mass. This was not the pole mass. This was the mass at the Z pole, right?
Yeah, this is really the mass which is. It's the mass, the kinematic mass, you could say, calculated from the decay products. Yeah. So you basically have top quark, it decays W boson B, you measure the kinematics of the B jet, you go back to the W mass from the decay products, and so you take this and then you calculate the top quark mass. This is what they did in the early days when it was good enough. But it's certainly not good enough if you do this procedure and then you quote such a number. This is not a realistic error estimate. Yeah? So this was then the main criticism that was voiced when it became critical. You know, if you do such an extraction and you get, say, 170 plus minus 5, it's good. But if you want to do precision physics and also then make precision statements about, say, the fate of the universe, then you have to go to a well-defined scheme and use typically differential cross-sections for that. And also keep correlations. So basically, this is also what experimentalists are also doing now. So suppose they have like a double or triple differential distribution with top quark samples, then they also do a correlated fit of alpha S. They also try to keep correlation with the PDFs, and then they extract the mass. So just to be sure that they have this all under control. You know, because I can basically shift the top quark mass to any value I like by tuning the gluon, for example. And this should not happen. So.
Like in fact, not just the top mass, you had even the alpha S value actually at some.
Yeah, also alpha S. I can also shift the top quark around by different alpha S values. So this is why it's important to really keep these correlations.
Related question. So you said, it's a Monte Carlo mass or whatever, from the. Is there a way to relate this mass to say mass defined in some other schemes?
Yeah, there is a line of research. This is mainly pursued by Andre Huang and collaborators, and they try to have a theoretically well-defined description of what happens in a part-on shower. So basically, then you start off with a quark, and you try to calculate in a theoretically well-defined way what happens with additional gluon emissions. You try to renormalize, you try to identify the scale at which this is happening, and then they try to relate this model of what is happening in the parton shower. They try to relate this to a well-defined mass, and this is they have succeeded in doing this I think for the Herwig parton shower. For the Pythia parton shower, I think they have not really succeeded in doing this, and in this way they then try to calculate a possible offset between such a Monte Carlo mass, in quotation marks, and whatever would be the pole mass or the running mass in a well-defined scheme. So there is also some research being done in this direction. But this requires also particular modifications of this Herwig parton shower Monte Carlo, so it's not yet at a level that you can really give this to experimentalists and say, look, use this and subtract maybe 2 GeV from that value and you have your pole mass. So we're not yet at that level.
Any further questions? I had a naive question here. So now with the calculation that is done for this stability of the electric vacuum, so it is now well established that it is a metastable vacuum? Because can there be any corrections from alpha S running, or because the alpha S running is only known up to 4 loops, I guess?
Right. So basically the effect of alpha S here, in addition, there is some effect, but this is smaller, I would say. So the main parameter which is driving this is really the top quark mass, and then I would say it depends a little bit on whom you ask. So this original formula had been derived by people who are working in BSM physics, and they were happy to conclude that standard model is ruled out at whatever 10 to the 11 GeV, but a more refined analysis, I think it puts us into this spot here, and I think this is subject to debate. Yeah, so I think it's fair to say we are away from the unstable region, but we are certainly, it's not yet settled that we are in a stable or not deeper in a metastable region. Yeah, so I think this is open. Yeah? If you look at all possible opinions, of course, I would say we are more placed here, but still, I think this is subject of further research. And this is also, if you look at the upcoming high energy run at the LHC, they will have much higher statistics for top quark data samples. So there is certainly a push also within the experiments to make new analysis, to have really precise measurements of the parameter there. So over the next, say, 3 years, we can certainly expect more results also there. If you wanted to have the ultimate answer, like with 100 MeV uncertainty of the top quark mass, then you would need basically an E plus E minus collider, where you have E plus E minus collisions, and you tune it into the top quark resonance, and then from the width of the resonance from the onset, then you would have a much more precise measurement. But this is, we are talking the far future.
Now that you mentioned this, there was some tension some years ago between alpha S from E plus E minus and alpha S from. Has that remained? Has it gone away?
Oh, this is still subject to debate as well. Yeah. So basically, we have we do see alpha S determinations, for instance, from lattice QCD. We see them from LHC observables. We see them from DIS. We see them also from E plus E minus. At the level of precision that we're working at the moment, we see within each of these determinations, we see differences which are bigger than the quoted experimental uncertainties, and those are mostly due to different theory assumptions which are being made in extracting such a value. So this is also telling you that we really have to be careful now if somebody gives you an alpha S value and it sounds odd to you, then you really have to look at what are the kind of theory assumptions that went into the extraction of this parameter. So we are when
program to try and verify all these results?
no, I think there is basically whenever there is a workshop with alpha S discussion, there are heated discussions because everyone defends his position. So I think, yeah, how should I phrase it? I think we, yeah. With a given accuracy of the data and a given status of the theory, it is hard to argue against each other. So you would make progress with more precision data and with, say, improved theory calculations. So one example is, for instance, if you do these PDF determinations, you can also extract alpha S as a parameter. And then the value of alpha S depends on whether you, for instance, include higher twist effects or you neglect them. So this is a systematic shift of alpha S. It also depends on what kind of assumptions do you make about a heavy quark part. Yeah? So if we would have higher accuracy for the heavy quark part there, that would certainly help in just eliminating one or the other uncertainty which is currently there, simply by saying this is the new state of the art of the theory there to use. Yeah? So this is, I think, the best way to try to improve the situation there. But yeah, otherwise I don't see consensus there coming up. It's more like heated discussions. Yeah.
The flat review, what did you do? Do you combine the data or do you just...
So basically what the PDG does, they basically look at these individual determinations and then they say we just combine the different determinations. However, if I can show to you that the differences come from different theory assumptions, some have included corrections, others have not, and then this leads to different results, then I would say it doesn't make sense to average over those two results. Yeah? Because you have to decide either this is wrong or this is wrong, yeah. And this is a discussion, of course, which is it is difficult to have among colleagues because everyone says I'm right. Yeah?
Okay, so I see no further questions, so I will thank again Professor Moch for this fascinating talk. And I will invite you for refreshments outside, and you can always discuss with him and ask him more questions over coffee. Thank you.